I just wrote this one a couple days ago, and I thought it was really quite interesting, and I've been cracking encryption in Android apps for years using this technique, and I realized it wasn't in my courses here, so it should be. This is the way you password protect data. This is the standard way to do it, for example, to encrypt a hard drive. Now, in the old days, like MS-DOS, you would log into a system, and it would actually have a password file on the system. You would type in your password, and it would look in the password file to see if you got it right. And that's, of course, a very dangerous system because you stored the password somewhere and someone could steal that file. Nowadays, logins use password hashes. And I've got projects up there where we crack password hashes, and I'll probably show you that after lunch. But this one is the alternative system where you want to, this is what iPhones use to encrypt an iPhone, and it's what virtual machines use to encrypt a virtual machine. You want to make it so you must enter a password to use the data, but you don't store the password anywhere. The password is used to create an encryption key, and you don't even have the encryption key until the correct password is entered. That's the trick here, and that is what this does. Password-based key derivation function. That's what this thing is. And so, it's in HashLib. So import HashLib, all right. In fact, I'm going to leave this and come back because I don't want to have that weird padding Oracle stuff in it. All right, so now Python 3. All right, and now import HashLib. All right, and here's help about HashLib. And if you go to the end, you'll find that there is a function, PBKDF2. HashLib can do this. So you give it the name of a hash to use, your password, and a salt. It's going to take your password and add a salt, which is just some optional random characters to add to the password. And then it's going to run this hash some number of times and extract a certain number of bytes from it. And that will be the random string created, apparently random string created from the password. That's PBKDF2. So here we go. If I use MD5 for the hash algorithm, and the password is Apple, and there is no salt, I can run this function, and I get this string, AA7272. You could use that for an encryption key. And by the way, it is not random. If I use Apple again, with the same salt and the same algorithm, I get the same answer again. So the user puts in a password, you run it through the algorithm to create the encryption key, and that's it. The key is not stored anywhere, and the password is not stored anywhere. Only by providing the correct password can the user get at the data. So that's pretty cool. And this is what's actually used by many systems, in particular by VMware and VirtualBox to encrypt virtual machines. So let me try this one. This is what's actually done in many, many systems. You use PBKDF2 and AES. So here, I import the libraries, and here's my clear text. All right, and I made it so it'll fit in blocks. Then I use this MD5 algorithm one round to create a key, and then I use that key to create an AES object, and I encrypt it with that key. So this is the encrypted data that you could store somewhere. And the only way to get that data is to enter the correct password. So that's the encrypted blob of data starting 68AA. And here I take the 68AA and read it into ciphertext. And then using the key, I'm able to decrypt it. So that's the plan. You can reconstruct your plain text. So that's the fundamental technique. And so I've got some challenges here, and you'll get down to encrypted virtual machines. This is what's used to encrypt virtual machines. And here's an article from Elcomsoft, I think, yeah, which is a Russian company that cracks all kinds of encryptions commercially. There's Elcomsoft, and there's the one in Israel, a famous one in Israel that the FBI used to buy software to crack into iPhones. And so virtual machine encryption parallels is incredibly weak. It uses AES CBC, but it only uses 2 iterations of MD5, pretty much what I'm demonstrating right now to encrypt it. VMware uses 10,000 rounds of SHA-1, and VirtualBox uses 1.2 million iterations of SHA-256. So there is a huge difference in the relative security of these, but they all use the same general procedure. And this is the actual key safe from an encrypted virtual machine I made. It stores this in the VMX file. This is the way you do it. You define a key safe, and this is also the way Android and iPhones do it. iPhones do it in hardware. They have a thing called the secure element, which is a special memory chip to store the key. Androids, many of them emulate it in software with a technique like this. They define something called a key safe, and in here they have the information about what they're doing. They call it pass-to key. Anyway, it's easier to format it a bit, and then you can see it here. This is the system, password-based key derivation 2, HMAC SHA-1, and then AES 256. It uses 10,000 rounds, and this salt in base 64 notation, and then this is the contents of the key safe. So you take that data and the password from the user, and if the password is correct, you'll get the key to open this safe, and in the safe are further secrets, like the encryption keys for the data. Cellebrite is the other company. Yes, exactly. Cellebrite and Elcomsoft are the experts at making these hacking tools. So this is the system, and this is the code that will decrypt the data. This particular virtual machine was encrypted with a password of 123123. And it stored this information. It added this salt. So if you know the correct password, you can decrypt the data this way. And here's what it looks like when you decrypt it. This is taking that data, which was created by VMware with this LZTE7, and I had to decode it from base 64 and turn it into bytes. And now I take the salt, which is also in base 64, and I do this SHA-1 10,000 rounds with the password of 123123 and salt, and I extract 32 bytes from it to get a 256-bit key, which is what's required here, because you can see it's using AES 256. And then I create an AES object using that. And the IV is the first 16 bytes of this, or the initialization vector, and then comes the data. And then I decrypt it, and here's the clear text. This is what was stored there. Type equals key, cipher equals AES 256, key equals, this is the start of a key. This key safe contained another key. That key was actually stored, but it was password protected. You couldn't get this key without putting in the right password. So that's the system, and I've got some challenges here. Here's a real one I made with a 6-digit password, but I repeated each digit twice, so there's only 1,000 possible keys, so you'll be able to crack this safe pretty easily. And here's a challenge that started it all. A student called me a couple days ago, said, can't we crack these? And he used an 8-character password. And by the way, the first 2 characters are WE, and the last 2 characters are SS, if you want to do this one. Otherwise, it would be impossible. I'll add that to the challenge. I forgot to put that in the instructions. So there's 4 letters to guess, and they're all lowercase. And that will still take some time. But anyway, you might check that out. This is how password-protected data storage is really done in practice.